reachable. Okay, this seems like an obvious, and in fact, mathematical induction, the principle of mathematical induction itself, is an axiom. Okay, it is not something that we prove. Okay, so here's another example, just to make sure that we're all on the same page. So you have a friend, his name is Pablo, and for whatever reason, he wants to color the integers. So you have 1, 2, 3, 4, 5, an infinite set of integers. So he starts coloring those integers. Now, you don't know what the coloring will be. You know, any integer can receive some kind of coloring, so you don't know what is in Pablo's mind. However, you're told that the first integer is for sure going to be blue. That's one piece of information that you're told, like a clue. We'll call this, in a minute, a basis step. Okay, base case or basis step. And you also have a second piece of information. And that second piece of information says that this is true for any of the integers. If that integer is blue, so for example 55 is blue, then 56 is also going to be blue. And that's true not just about 55, but it's true for any integer k. You name the integer, and if that integer is blue, notice we're not claiming that that integer is going to be blue or anything like that. We're claiming that what we know is the implication itself. And in a second, I'll ask you a couple of questions that you may remember from logic. Okay. So pick any integer k, and if it is the case that that integer has the property of being blue, then so it is the case that the next integer over, the k plus first integer, has exactly the same property. Okay, so we're talking about an implication here. So now, while we're at this topic of implication and so on and so forth, can you please remind me what is a predicate? First of all, what's a proposition? What is a proposition from logic? Can people help me out? I forgot the terms.
Is it a statement that's either true or false? Is that what it is?
Yeah, that's exactly what it is. That's a proposition. A proposition from logic is simply a statement that can take only one of two possible values. And those values are true or false. Okay, fine. How about a predicate? What is predicate? So you've considered in logic in 1166, you've considered propositional logic, then you talked about predicate logic, first order logic, and so on and so forth. So what is a predicate?
Isn't that Boolean logic?
Sorry, one more time, please.
Boolean logic?
It is a Boolean logic. All of the the term Boolean refers to all of it in some sense, right? In the sense that Boolean means two values, either true or false, either 1 or 0. So Boolean value is the true or false value. So yes, it's all Boolean logic. Okay, that is true. But the term predicate itself, what does that mean? From logic. So predicate. Okay, so we don't want to get bogged down with the terminology itself, but I think I'd like to mention it still. The predicate, it has the same meaning as what your English teacher would ascribe to it. So like an English teacher, say somewhere in middle school or high school, would have told you a sentence, so there's a subject in the sentence and there's a predicate in the sentence, and they would tell you a subject is what the sentence is all about, and the predicate is what is being said about the subject, blah, blah, blah. That's exactly the sense in which we take the predicate. The predicate is what is being said about something. So you can think of it as being a property of some entity. In our case, the entities of interest, or the subjects of the sentence. The entities of interest will be integers, like integer n. So what we will be proving in what's to come is that all integers, n is a generic reference to an integer, okay? That n can be anything. So all integers have some property p. That p is the predicate. It asserts something about the integer, that integer has a property. For example, in this coloring example, that property is that the integer has the color blue. In the rung example, is that rung is reachable by that guy who was climbing the ladder, and so on and so forth. Okay? So n is the property of being blue. It has the property of being blue. That's what p is in this example. It's a predicate. Okay? Now, one more thing before we move on to concrete examples. I'd be remiss if I didn't mention that very often the idea of induction is introduced by using this picture of dominoes being knocked over. So you have this infinite sequence of dominoes here, and P. What is the predicate that's being asserted about the first domino? That it can be knocked over. Okay, you knock over the first domino, and then you also know that if some domino gets knocked over, okay, and then the next one over will, the one to its right will also fall, right? That's what's called the inductive step. So if I have these two steps, the basis step and what's called the inductive step, that is, if I knock over the kth domino, then the k plus first domino is going to be knocked over as well. That's called the inductive step. Then what we conclude from this, that all dominoes will be knocked over. Okay, so that's the principle of induction. Okay, kth domino falls, knocks over the k plus first. If that's true for any k, then any domino would fall over. Okay, so here's the statement of the principle itself of mathematical induction. You'd like to prove some proposition, P. Well, so I will, okay, it's actually predicate, say, some proposition P. By the way, notice that these propositions, it is really a propositional function, take this predicate, in the sense that we're proving an infinite number of propositions. And you know, it may strike you as strange that we're using a finite time, so in a few minutes, we're proving an infinite number of propositions. What are the infinite number of propositions? All these propositions, P, that we're asserting, they're indexed by n, by some integer. So think of coloring those integers. We're proving an infinite sequence of statements. We're saying that integer, any integer, has the color blue. So that's true for 55, 56, 57, gazillion 17, and everyone else. An infinite set of propositions. To prove that this proposition is true for every integer n, we have two steps. One, what's called the basis step. We're simply proving that the proposition is true for the first integer. That's called the basis step. And we also have an inductive step. An inductive step involves showing the implication itself. Now, notice at this stage, and I know we haven't looked at particular examples, but some people, this may strike some people as a classic example of circular reasoning, right? You may object, look, isn't this what we're about to prove? We're proving that some predicate holds for this n, right? So for every n, we want to prove this for every n. And look, here are you trying to fool me or what? You've just changed the name of the variable p of k. And you're saying that assuming that pk is true, you want to show that pk plus 1 is true. How do you get to assume that pk is true when it is what you set out to prove? You wanted to prove p of n. You just change the name n to k, and you know what's happening. It's kind of not clear. So we'll clarify this, and it will be clearer with the examples. But let me just mention now one thing. Just let me see if we can recall something from logic again, just to be clear what it is that we're proving. This is kind of an aside. So do people remember these logical connectives that you had from logic? You had P, let's say P and Q, or some propositions, any propositions in logic. And you said like P and Q. You wrote things like P or Q. I don't know the way you wrote it, maybe like this, right? P or Q. You had P implies Q, right? So what you did in logic, you wrote down P, you wrote down Q. Okay, these are two propositions. And each one of those propositions could get either a true value or a false value, right? But the pair of propositions, P and Q, all possible values that these propositions could take would be something like that. There are four possibilities, right? Okay, so these are all four possibilities this pair of propositions can take together. And then you gave definitions for the connectives. Those were the definitions. For example, you defined what does it mean to say P and Q. Then you defined what does it mean to say P or Q, or P implies Q, or something like you had one, what you called probably a monadic connective, which was not P, for example. It simply flips the value of P. If P was true, it made it false. And if P was false, it made it true. But anyway, you had this implication as well, P implies Q. Can somebody help me out? What was the value of this implication? So the big deal probably made in the logic section of your 1166 was that, okay, so you have these, you probably call these atomic propositions or something similar. So P and Q, so these are propositions. And then I can build more complicated, call them molecular propositions, like P implies Q. And those themselves, like the entire thing, P implies Q, that itself has a single value. That implication itself is either true or false, right? So what is the value of this implication? So, and that was the whole thing about filling out those tables, right? So you had more complicated tables in this, but I'm simply asking for this implication. What does it mean to say P implies Q? What's the value of that implication? So you filled out entries in the table, like on homework questions and maybe quizzes. So can people help me out, fill out this table?
True, false, true, true.
Yes, exactly. So notice that it's only false in one case, right? It's only false in one case here. It's only false when the antecedent is true and the consequent is false. Okay, maybe I'm throwing terms again. It's not that important. P in this context, P implies Q. P is called the antecedent and Q is called the consequent. But the terms themselves are not important. What's important is that in the implication, I get the entry false only in the case when P is true and Q is false. Right. So for P implies Q, when P is true and Q is false, I get this entry false. Otherwise, it's true. Okay, so here it's true, and everywhere else it's true. Now, why do I bring up this table? This is because the principle itself, the principle of mathematical induction, right, the axiom of mathematical induction, wants me to show that this implication itself is true. What I'd like to draw people's attention to is that I only care about this implication to prove this implication is true. So I want to show that pk plus 1 is true whenever pk is true, right? I never care for the case where pk is false, because whenever pk is false, here and here, no matter what, pk plus 1 stands for q. So I wrote down for p, this is p of k, big P of k, this is my proposition p here, and q is that. So I'm talking about, just to be clear, this implication. Just clear up a little bit. Okay, so this implication here, this is P, this is Q. Okay, so in this table. All right, so if P sub k, which is my P, is false, okay, no matter what Q is, no matter what pk plus 1 is, the implication itself is true. Okay, so what I'm trying to show that the entire implication is true, my only concern is that I don't get this case, this pesky case here, this case. I don't want this case to happen. I don't want this row to happen. So what I want to show for the implication, I want to show that the implication is true. So what I'm concerned about is showing that every time P is true, Q is also true. So I'm concerned about this case, this top row here. I want this to never happen. Okay, I want this to never happen, that row. I don't want P to be true and Q false, because in that case, the implication will be false. Okay, that's not good. Okay, so good. I made a big deal out of it, and now this may come up. Let's get to concrete questions now. Okay, any questions so far? Let me just recap. At the end of this class, I will give you. Okay, some people have asked for concrete steps, right? So we'll give you very, very concrete steps and what to do. And once you have these concrete steps, in fact, once you grok this notion of, and it's easy to understand, granted, like this whole idea, it's like you have two steps. You know, you're proving something for an infinite set of entities. You prove something for the first one, and then you prove this inductive step, and then you proved that something for an infinite sequence of entities, okay, for integers in our case. So that's kind of easy to understand. But you'll see that there are some quirks that may come up. Okay, so let's just start proofs by induction. Prove that the sum of the first consecutive n integers evaluates to this. Well, what does it mean? Well, first, you see a problem like this, the first thing to do is check whether whatever you're asked to prove is correct. Does it work for a few cases, right? So let's see. What happens when n is 1? Okay, that's case 1 is 1. What does this expression say when n is 1? What do I have on the left-hand side? Here, when n is 1. Do I have 1 on that side? So help me out.
0 plus 1?
Sorry?
0 plus 1?
Well, where does the 0 come from?
N minus 1?
Okay, all right. Okay, so okay, I'll get back to that comment. That's actually a good point. That's actually a good point. What we're saying here is that when n is 1, there is no n minus 1 here, right? There's no n minus. When n is 1, I have 1 on the left-hand side. Can we agree that this notation means that? Can all of us agree that there's no n minus 1 in that case? Can we make this agreement from now on so that there's no confusion? So that's the agreement. Is everyone okay with this?
Yes.
Okay, then if we agree that this means that n is 1, this piece is 1, what's on that side? That's more straightforward because it's an expression. What does it say? N?
Plus 1.
Yeah, 1 plus 1 over 2, which is, okay, which is 1, right? So I have 1 equals 1. So, okay, that's probably a trivial case, but what this says is that this claim, when n is 1, so p of 1 is true, I've just proved. So p, what is p itself? Okay, we'll see that in this class, you'll be asked to explicitly write down that p in the proofs. So proofs will have a very clear-cut format in this class. So you'll be following the same format when submitting proofs by induction. Anyway, we've just checked that this works for n when n is 1. How about when n is 2? What does this expression say then? What's on the left-hand side? Can we agree that that's what's on the left side? And what's on the right-hand side?
3.
Okay. So on the right-hand side, I also have 3, right? So I have 3 equals 3. So the expression works. Let's check one more real quick, just to be sure that what we're proving is true for a few values of n. So when n is 3 on the left-hand side, I have 1 plus 2 plus 3. And on the right-hand side, okay, on the right-hand side, I have 3 plus 1 over 2. Okay, what is that? Okay, is this 6? On this side, 6 equals 6, right? So the point is that this happens to be valid for a few values of n. But of course, this is nowhere near being a proof. We've just checked a few cases. So how does one prove that this is true for every n, no matter what n? Obviously, there's not enough time in the finite lifetime of a human being or of the universe to prove an infinite number of statements. This being true for every possible n, right? So, but it's still possible to prove using induction. Okay, so I'll give a proof. Now here's what we'll do. So now, again, nobody doubts that for a few values of n, this just happens to be true. So now we'll prove this for every n. We'll outline the steps here on the next page. I'll write down the proof exactly the way that you'll be asked to submit proofs by induction. And then we'll write a version of the proof that you will submit. Okay, so we'll go through this in detail. A couple of the first 2 or 3 examples we'll do in very much the detail. So here's what the steps of an inductive proof will be like. Okay, at the end of these slides, you have a summary of these, but in this particular example, here's what we'll do. First, always, the first step is to identify what my predicate is. What is it that I'm trying to prove? Okay, usually, like in this example, the predicate is easy to identify. So what is it? What is the property about the number n here in this example that I'm proving here? So let's translate this into predicate logic. And then later we'll translate the whole implication into predicate logic. So what is the property P that I'm proving about the number 55 or whatever, about 2166? What is P? What is P 7, let's say? What is that?
7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1.
Yeah, exactly. So P, the property of the number 7 is that the sum of all integers beginning from 1 and up to 7 inclusive, that sum of the first 7 integers, the sum of the first 7 integers can be computed using this expression. That's the property of the number 7. So now we're going to prove that same property for not just 7, but for 8 as well. Okay, and for 55 and every other integer in the world. Okay, so we'll identify that. We'll write it down explicitly in a minute. Then, okay, so then we'll say, what is it we're trying to prove? We'll try to prove that Pn, once we've written down what Pn is true for every n. That's what we want to prove. And then these are the 2 most important cases. Okay, the first one will be called the base case. You prove that P1 is true, which we actually already proved up here somewhere. Okay, here we proved that to be true, but that is something that will be included in the proof in a minute. And then we'll prove the implication, which you will help me do. See exactly what's involved there. So this will be the meat of the proof. This will be the heart of the proof. Okay. And finally, you will say that because you've established the basis case and you've established this, by the way, this is called the inductive step. Okay. And in this implication, which we're trying to prove, pk, this is what we'll be trying to prove. Pk implies pk plus 1. In this context, that pk is called the inductive hypothesis. Okay, so you can call Pn itself, and you can call it's indexed by a different variable here, n, but it is the inductive hypothesis. Anyway, once we have these two facts established, that the basis case is true and that the inductive step is true, that is, the implication is true, then we'll write the final sentence. Therefore, by the principle of mathematical induction, the statement has to be true for all n, and that concludes the proof. And that will be my proof by induction. Okay, so that's what's coming. So now let's get started. Now let's neatly write out the proof. So this is the proof. The first thing I write down, and the first couple of examples I'll do in detail, you write down in words. The proof is by induction. Now, granted, is by induction. By induction. Granted that if you're asked to provide a proof by induction, you don't really have to write down this sentence. But you normally would if you're just proving something generally to somebody in some paper somewhere, and you're just alerting the reader that what's coming is going to be proof by induction. And of course, your reader is familiar with the proofs by induction. So you're just simply communicating your proof. And you're alerting them to what's coming. You're telling them proof is by induction. Okay. The next statement, the next sentence, rather, let's call it, in your exposition here, that is in your proof, in your little essay, and proofs are little essays, okay? So you tell them what your inductive hypothesis is. So what is it that you're trying to prove? That Pn, what proposition, and I'm using here the term proposition, I should really be saying predicate, but okay, I'll be a little loose here. Let Pn be the proposition, 1 plus 2 plus n equals n times n plus 1. That is exactly what I have above. So in this case, in the first few simple cases, my propositions will be exactly these, what I'm trying to prove. Okay? So later, maybe we'll see examples like where the statement of the claim itself does not involve any numbers, and somehow we'll have to translate them into something numerical so we can identify the proposition P of n and then prove it, and that somehow connect that to the statement of the problem, and so on. But let's not deal with those complications for now. Okay, so let Pn be this proposition, right, for any given n. So to show that Pn is true for any n, we proceed by induction. Okay, so we write some little, okay, we want to write every sentence, but to show that P of n is true for any n, greater than or equal 1, right? We prove the base case. We show that the base case is true. Show that the base case or the basis step, and the inductive step, the basis step is true, and the inductive. Okay, let's pull. Okay, this is a bad English sentence, but it's a active step are true. Okay, true. Okay, so here's the basis step. What's the basis step? P of 1. We just proved it. Basis P1 happens to be true, is true because 1 equals 1 times 1 plus 1 over 2, that's 1. So basis step is usually simple to prove. So right, so what I did here is this 1 comes from this piece when n is 1, and this piece, the right-hand side, comes from this piece when n is 1 also. So that holds. Now, inductive step. To prove that implication, we assume that pk holds for any k. Pk is true. So notice that I'm assuming, I'm not saying that P of k is true. That would be a classical case of circular reasoning. The logicians call it circular reasoning. What is that? I'm trying to prove Pn, and now I'm assuming Pk is true. What on earth is that? No, that would be wrong. But I get to assume that Pk is true in the context of proving the implication. I want to prove that Pk implies Pk plus 1, and therefore this is not circular reasoning. So I can say, assume that Pk is true. Then we'd like to show, prove that then Pk plus 1 is also true, So that would prove that Pk implies Pk plus 1, and that is exactly what my axiom of induction asks me to show. And if I do show this, then I'll be done. Is also true. Okay, so now help me out. Okay, so now I'm proving this inductive step. We're going to have to move to the next slide. Okay, let's use some other color. And here, let's say you're facing a problem like this on a quiz or somewhere in a homework question. The first thing to do is to write down the expression for pk plus 1. So we'll have what we'll call Simpson's cloud. So here's Bart Simpson. And this is not part of the proof. This is like scratch work on the side. Just to make it clear in your mind's eye what it is that you're proving here. So what is pk plus 1? Let's write down pk plus 1. What is it, pk plus 1? What is that? What does it mean to say pk plus 1?
Like the next value after pk, which is the one you did up top there.
Yeah, but that's true. But so how do I write this down explicitly? What will be, what is exactly that I'm proving? Like what is pk plus 1? Pk plus, so this here, like take this one. This is p of n. So in terms of n, so here's my n. P of n is, okay, p of n is that the whole thing, this equality holds for any n. That's p of n. So for any n, right? Pn is true. Pn is true. True for any n. For any n is this. That this equality is true for any n. So what is that when I have k plus 1? So what is this equality? Let's write it down. 1 plus 2 plus blah 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 plus k plus 1, right? Is k plus 1, k plus 2 over 2, right? That's what it means to say pk plus 1. pk plus 1 is this equality, the equality. These two expressions are equal. That's pk plus 1. The left-hand side and the right-hand side. This is what we want to prove. But we get to assume that pk is true. What is pk? We get to assume, this is all scratch work. Get to assume, this, my proof is upstairs in the previous slide. Get to assume p of k. What is p of k? That 1 plus 2 plus k is k times k plus 1 over 2. That's what pk is. So I get to assume the purple one. And with that assumption, I will be proving the red one. This is the red one, and below is the purple one here. So I get to assume the purple one. So why is the red one true? So why is that the case? Here's, and I'm coming back to my clean proof. Inside the clean proof, when I'm writing all these sentences in English, now I have to justify why it is the case that 1, so let's use a different color. So why is it that 1 plus 2 plus blah, 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 plus k plus 1, okay, will end up being, okay, somehow I need to prove that this will end up being this. Why is that the case? Now let's justify this algebraically. Well, this piece, by the inductive hypothesis, I'm going to say, so what's the inductive hypothesis? Help me out. I'm going to write down that this piece, plus 2 plus k, this piece, is going to be k times k plus 1 over 2. The other piece, k plus 1, I'm going to write down as is, right? So am I justified? Because I'm not doing any like thinking here. All I'm writing down is just I have an expression. I'm trying at the end of the day, I want to show that this is going to be equal to this. But I don't have that yet. That's what I'm trying to show. That's why I have a Simpson's cloud. This is what I'm thinking. This is where I want to get to. But I certainly can write down what I just wrote down here, right? That I can write down, right? Do people see why I wrote this down? Well, it's worth pausing here for a second. And then we'll come back and look at the entire proof in a second. Okay, let me continue. But this is the same as, okay, k plus 1 over 2. I'm just rewriting this, which I know to be true because that's the red piece here. And the black piece I'm going to write down as 2 times k plus 1 over 2. Okay. Then I'm going to need some space. So what I'm going to do is I'm going to take all this stuff and move this away right here. Okay. Okay. So continuing here. This is equal to k plus 1 plus 2 k plus 1, right? which is the same as, well, common factor k plus 1, and I'm left with k plus 2 in there, divided by 2. Okay, so that's just algebra. So all these pieces like this, all these equality, all these equals, that's just algebra. There's nothing interesting there, just algebra. Just algebraic manipulations. So, okay, so what happens? What am I concluding here? Have I just proved the implication that pk does pk imply pk plus 1? Okay, does pk imply pk plus 1? Have I proved it? Well, yes, I proved it because I've shown that pk plus 1 is true. I've shown that we just showed that pk plus 1 is true. pk plus 1 is true. Okay, where did we show it? Well, here. This is here with the Simpson. Well, now we just moved away that Simpson, but this is what we wanted to show. That this was going to be equal to this, This was going to be equal to this. Right? That's what we wanted to show. And we did show that. And in the process, the only reason we were able to show that is because we got to, maybe not the only, because we got to assume the PK, the inductive hypothesis. By the inductive hypothesis, we had one piece that was definitely true, right? Okay, so now am I done with the proof? Yeah, actually I'm done with the proof, but I have to write a couple more sentences just to make my write-up clear. Okay, so what we've done so far is we've proven the base case, and we've proven that pk implies pk plus 1. In the final sentence, I say that therefore, by the principle of mathematical induction, Pn holds for any n, is true for any n, And that completes the proof. That's my QED. Or instead of QED, you write like a little square. That completes the proof. The end of the proof. QED is the end of the proof. That which needed to be demonstrated in lab. Okay, so any questions about this? If there is a little feeling of uneasiness, that's fine. Now it's time to do another example. Okay, now help me out. So again, let me jump down real quick to the steps that I'm going to give you. So we'll still have to do a bunch of these examples. So here are the steps. At the very last slide, you have the steps and what to follow. Every proof by induction in this class. So these are what we'll call simple mathematical induction. So we'll have another notion of strong mathematical induction, not because this is simpler than the other version. They are equivalent, and we'll show that they're equivalent. But just to distinguish one from the other. This one is called simple mathematical induction. So we'll get back to that. These are the steps to follow each time you're making a proof by induction. Okay, and these were the steps we just followed in this proof. So this will be at the very end. I'll come back when it's time, the last couple of minutes, when we summarize everything. But for now, we have to do another example before we leave. So let's just do another one. Now you help me out this time. So remember, can anyone help me recap the steps real quick? So what are we doing? What are the main steps? So now we'll do another example. Yes.
You evaluate at the first integer, whether it's like 1 or whatever, and then you do it for n, and then you do it for n or k rather, and then k plus 1.
Mm-hmm. And from these two steps, we conclude that whatever we wanted to prove is true for every n. That's exactly right. Yes. Yeah. So now let's see. Let's just prove that was example 1. Now, by the way, proofs by mathematical induction often provide zero insight into the nature of the problem itself. They tell you absolutely nothing. Now, we proved that the sum of the first n integers was n times n plus 1 over 2. Did it give you any insight as to why that was the case? No, not at all. It's not there are plenty of very nice proofs of what we just proved by induction. And if we have time, then I'll give you a nice proof, let's say a geometrical proof, a couple of proofs that are elegant, at least. There's nothing elegant about mathematical induction. It's a streamlined procedure. You do this, 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 this. There's one moment where you get to exercise creativity, maybe, depending on the problem. And that's in the inductive step when carrying out proof by induction. And, well, depending on what the problem is, it actually can be quite interesting, the application of the principle itself to the problem. So we'll see maybe on Monday a couple of examples like that, where Okay, so we'll see more interesting examples. For now, let's just do straight problems, like proving something, some property about the integer n. Okay, first, here we're asked to conjecture something about the sum of the first n positive odd integers. So we're not given an explicit formula. We're asked to actually come up with one. Okay, so inductive proofs are great when you've actually already had the insight. You've done all the mathematical work, you're doing the creative work you're doing before proving this by induction. So, okay, let's see if we can figure out what they are asking us to do. So, what? First, n positive integers. I don't know. All right, let's write down n positive odd integers. Okay, 1 is odd. Well, that equals 1. The first two, 1 and 3. These are the first two odd integers. Well, that's 4. First 3 odd integers. That's 1, 3, and 5. Well, that looks to me, what is that? That's 8, right? Or 9, right? 1 plus 3 plus 5 plus 7. What is that? Okay,
16.
What is 16, right? I think. Okay. 1 plus 3 plus 5 plus 7 plus 7 plus 9. Oh, that's 25. Do I see any pattern? I don't know. Here's one more. 1 plus 3 plus 5 plus 7 plus 9 plus 11. That's going to be 36, and so on. Do I see a pattern?
Yeah.
Yeah. What is it?
They're all squares.
Yeah, exactly. So this is 1 squared, 2 squared. The first 2 integers, 2 squared. The first 3 integers, 3 squared. The first 4 integers, that's 4 squared. That's 5 squared. That's 6 squared, and so on. Okay. So far, now I'm beginning to have suspicions. It's like a mystery of some sort. Okay, so some detective is getting hunches, suspicion. Now, there's no proof. Okay, so this is like we're beginning to suspect that that's the case. Now comes the part that this class is about. Now prove that this is the case. This is how you prove program correctness, for example. Okay, so some of you who have covered recursion in programming classes can already feel that this induction business feels a lot like recursion discussions in programming classes, right? Okay. Okay, so let's, I don't know, what do you do with this? All right, let's forget about it then. Okay, so now let's prove this. That's our conjecture. So let's write this down. So the next step is what? To convert this into a mathematical statement that we can actually prove. So what is Pn? So we proved the conjecture. Conjecture was the sum of the first odd integers is n squared. That's the conjecture. Is that the sum of the n positive integers was n squared. This is what we suspect is true. So proof is by induction. It's by induction. Let Pn be the proposition. What is the proposition? Should I say predicate, but okay. Be the proposition okay, so what is Pn? So I should be able to write this down as an expression so I can prove it. Just as we did before. Like the earlier example was simpler because they just gave me the formula. Now I have to write down the formula. I'm suspecting what the formula is, but so far I have this in English words. Now I have to write this down and as a mathematical expression that I can prove. We give a computer to prove, by the way. This could be streamlined using a computer. So I need to write down that expression. So, okay, so what is it? What should I write down? 1 plus 2 plus 3. That's 3 squared. What should I need an n there somehow. So what should I say? N squared equals what? 1 plus, oh, why did I say 2 here? Again, 1 plus 3 plus 5. That's 3 squared. So 1 plus 3 plus, what should I put here? First of all, it's going to be an odd number. Is it 2n minus 1? People agree?
Yeah.
Yes.
Okay. So just to be sure that everyone agrees with this. So this is when n is 1, n is 2, n is 3, n is 4, n is 5. Just check a couple of cases. So this is 2 times 2 minus 1. This is n. This is 2 times 3. This is n. Minus 1. That's the 5. This is 2 times 4 minus 1. That's the n, and so on. That's the n. Anyway, that's my expression. That's going to be my Pn. Okay, so it took me some effort to figure that out too, but that wasn't really figuring anything out. It's just recognizing what this stands for. That's it. Okay. Okay. So let Pn be the proposition. 1 plus 3 plus blah blah blah. The dangerous dots, and we haven't seen why that's dangerous yet. We just got a hint of it though. Equals n squared. It's dangerous because I have to read in something in these dots. Okay, we'll get back to that danger next time. All right, so that's my Pn. That's the proposition that this equality holds. Now I want to prove that Pn. Now I want to prove that Pn holds for all n. Pn holds for all n. That's my. So what I wrote in purple, that's the inductive hypothesis, what the n mean variable. To prove that Pn holds for any n, we proceed by induction. Proceed by induction. Induction. Okay, so the basis step. You write down the basis step. What is P of 1? I'm claiming that it is true, and you tell me why. Because? Why is it true?
It's 1, so it's like 1 squared is just 1.
Yeah, 1 squared is just, okay, I should write, yeah, you're correct. I should write it the way you told me. 1 equals 1 squared, so it holds. So it's true.
Yeah. The first one was the first thing, so I would just plug the first one into the template, and that's how it worked. That's what I.
Yes, you are correct, absolutely correct. Then I don't know what I am saying then. You are absolutely correct. Maybe I was not misunderstanding. Yes, for n equals 1, but I just have this 1 and this 2n minus 1 when n is 1. It's the same entity in the sum. It's just I have one term. Okay, so if we agree on that, then there's
yeah, I agree on that. Maybe
okay.
I said it. I don't know.
Yeah, no, you're absolutely correct. This is absolutely correct. So, but you agree, but everyone agrees though that this step, the basis step is just immediate. So we have that on the left-hand side we have 1, and on the right-hand side we have just 1 squared, which is this 1 squared here. So 1 equals 1, therefore the basis step is done. It's the easiest thing to prove in the world. 1 equals 1, right? Okay, now comes the inductive step where I'll ask for your help because I'm lost, okay? But I'll write down, I'll tell you where I'm lost though. I have to be clear what I'm asking you. So inductive step. Inductive step. The inductive step, so let the inductive hypothesis, what is the inductive hypothesis? So we want to show, just to be more clear, we want to show that, okay, P of k, for any k, P of k implies pk plus 1. To do that, okay, that's all of this, that's why we had all this long discussion about logic and blah, blah, blah. So to do that, to prove this implication, so assume P of k, pk is true. So let's assume that. And from this, we want to conclude that pk plus 1 will be true. Okay, that's easier said. Now it's easy to say this. I mean, maybe you've done this in high school, maybe you've heard this a gazillion times. But let's this time just be clear why we're doing this. So let's assume pk is true. Now I want to prove. Now consider pk plus 1. So write down the expression. What is pk plus 1? So again, now I want my Simpsons cloud here somewhere. Here's my Simpsons cloud. So what is pk plus 1? What is that? That is 1 plus 3 plus 5 plus 2k plus 1. Am I correct? Equals k plus 1 squared. Is that my pk plus 1? I erased the whole thing. K plus 1 equals k plus 1 squared. Is that my pk plus 1?
Yeah, I agree with that.
So do people agree? So what was pk, just to be clear? So let's use a different color. pk was this. 1 plus 3 plus 5 plus blah, 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 2k minus 1 equals k squared. That I get to assume this. Now with this assumption, I want to show that pk plus 1 is true. Okay, so let's write down pk plus 1. So here's my pk plus 1. 1 plus 3 plus 5 plus 2k minus, let's write down the previous term and then the next term plus 2k plus 1. Okay, so these are dots here. These are dots. I want to show that this is going to be equal at the end of the day to k plus 1. Although right now, I don't know that that's the case. That's what I'm trying to prove. This is what I want to show. So I wrote down the left-hand side of what I'm trying to show. Okay, so now let's see what the red piece. I'm going to say that the red piece is going to be k squared. What I'm about to write, and I haven't finished writing down this line, but this is going to be by the inductive hypothesis. This is true, hypothesis. It's going to be k squared plus 2k plus 1. Now, people have to sort of say something about this. Do people agree that this is the case? Right? Because the red piece comes from the inductive hypothesis. That I get to assume to be true. If I got to assume to be true, then the rest is just algebra, as will almost always be the case in the homework assignments, and certainly in the quizzes. So the rest is algebra. So you just have to clearly identify where's your inductive hypothesis piece. So here's my inductive hypothesis. And now I'm going to ask for your help, because you were in high school like 2 seconds ago. And for me, that was like 20 years ago, right? So your high school teacher made a big deal if you forgot that this expression was true. If you somehow didn't say that in middle school or something, that this was true, you got in trouble for that, I think, in a math class or something like that, right? So if you said something like a plus 1 squared, that's a squared plus 2 times a times 1 plus 1 squared. So you said that. So everybody, so that you helped me out with that, right? So what does this stand for here then? Simply in place of a, I have this k. So do people agree that's this is k plus 1 squared? Right? So now, and I'm done. And I'm done by algebra. I've just proven the inductive step, because if I got to assume the inductive hypothesis, which is the red piece, if I know that the red piece equals k squared, then the entire piece, it has to equal k plus 1 squared. And that is my expression pk plus 1. And that's going to be pk plus 1, which is what we set out to prove, which was what we wanted to prove. Because we wanted to prove that pk implies pk plus 1, and we just did. We just showed that pk plus 1 holds. And we showed that it holds by using this assumption, which is our inductive hypothesis right here. Okay, so that's proof by inductive. Okay, so I'm not done. There's one last sentence I have to write down in my proof. Then it doesn't quit on you. Okay, now it's better. So the last sentence says, so therefore, by the principle of induction, by the principle of math induction, P of n is true for any n. True for any n. And this concludes the proof. I write my QED, which is, and nobody needs to remember this or know this, but it's quod erat demonstrandum, which in Latin means that which needed to be demonstrated. Okay, to demonstrate in the old times meant to show, to bring before one's eyes. That's what demonstration was. So, and then mathematicians concluded their proofs by putting down this QED. Okay, so in the Scholastic times, that's how people wrote this stuff in Latin, so that nobody could read, probably, right? So today people write this, or just simply write this like I don't know, maybe use this square, just something to indicate that you've completed it, or just write the sentence. This completes the proof. That's what people do, I guess, most frequently. And this completes the proof, and that's it. Okay. So that's it. That's induction. Okay. Now we have only done 2 examples. Now we need to do a bunch of more, a lot more, a bunch of them next time. So we'll get back to this on Monday. We just barely scratched the surface, and then we'll see that induction can be used also to prove more interesting things. Not that these are not that interesting, but other things that may not have explicit numeric expressions. It's something like the book has a nice example about like like pie throwing contest or whatever. So there's a bunch of examples that don't immediately explicitly don't involve numerical expressions, but can be translated into mathematical statements that can then be proven by induction. All right. So any questions so far? Okay. Let me go back to Canvas. Please read chapter 5.1 and start making sense of it. Right. Chapter 5.1 should make sense, and that's the basics of induction.